All right. Well, welcome back to the latest episode of the View Dependent podcast, where we speak to leaders, researchers, and creatives within the world of 3D reconstruction. And today, I'm really excited for the episode where a little bit earlier on, we spoke to the team behind the paper duster, which introduced this method, which shouldn't work. It shouldn't be possible. But what it does unlock is a lot of really, really great applications. And today, we're speaking to two authors who are starting to build on top of that duster framework. So I want to introduce Jun Yi as well as Kung Yi from both Spanner and Monster. So thank you so much for joining us today.
It's super exciting to have you both here because now we can see works that's building on top of duster. So for one, we will have a dynamic case where you can reconstruct dynamic scenes. And on the other hand, we will have a continuous case where you can just reconstruct like in a slam manner a scene, which is very exciting. And also, I'm really looking to have you here on the podcast because it's a lot of fun to see just projects popping up and using what's out there. So my first question would be, can you introduce yourself? What's your background? Maybe we start with Hengi.
My name is Heng Yi Wang. I'm currently a PhD student at UCL working on 3D reconstruction and VR rendering. I'm supervised by Professors Lourdes Agapito and previously completed a master in computer graphics at UCL as well.
And you, Yunji?
Yeah, cool. Thanks. My name is Jun Yi. I'm very happy to be here. So I'm currently a first year PhD at UC Berkeley. I'm working with Professor Trevor Dario. And my previous background are mostly in like 2D representation learning and also working with diffusion models. And it's a little bit funny, like this is my first project like dealing with 3D and 4D.
Very interesting, yeah. Maybe you could give us both an overview of your methods, what your work is all about. So before we start diving deep.
So for me, Spanner is kind of like a 3D models, a feed-forward models, where you take RGB images in and directly give you the 3D reconstruction in real time. And it's purely based on single forward paths on our transformer neural network. So it's kind of like, so previously for the 3D vision community, people will think that camera pose estimation, scene reconstruction is a chicken and egg problem. But for us, we kind of like do the reconstruction in a auto-regressive manner so that we don't actually estimate the camera pose. We just directly do the reconstruction incrementally. And yeah, that is basically the concept of Spanner.
So for Monster, we are trying to dealing with estimating the geometry from a dynamic scene. So what will be given will be a casual video, a marker video of a dynamic scene, and we're trying to reconstruct the per frame geometry, which is basically a point cloud, and also the per frame camera pose, like the extrinsics and intrinsics. So I think this is a pretty hard problem earlier, and people are mostly dealing with this problem with heavy optimization-based methods, which is pretty slow. And we are leveraging the duster, and we can try to do it in a like mostly free-flow way.
Brought up duster, and so because it's such an important part to the foundation, would you mind just giving a quick overview of like what duster is and why it's so important?
So I think duster is kind of a data-driven like multi-view stereo method. So I think it is powerful in that it can dealing with many unconstrained stereo inputs. So in our case, we are leveraging this robustness or generalizability of the duster model to dealing with unconstrained stereo inputs. So we are being given like two views as input. This is also the same for the duster. We'll be given like two views as input, and we can try to reconstruct this 3D structure under the same camera coordinate. So that's this meaning assuming that the given two views are the multi-view of the same static scene, but we extend the duster's ability to dealing with like dynamic scenes. So in our case, the two views will be the different time step of the same dynamic scene.
For me, I think Duster is kind of like it conceptually similar to end-to-end self-driving cars, right? So you basically your cars get some visual observation of this world, and previously you got a lot of policy or regulation to a lot of manual efforts to make it converted into control signals. But in end-to-end self-driving cars, currently they kind of like think that we only want one neural network, and you give my visual observations, and I directly map these visual observations into some control signals. And I think that's just share some similar concepts. So previously, if you want to from visual observations like images to 3D, you kind of like need a lot of sub steps, like a lot of manual efforts, like key point extractions, matching, sparse reconstruction, camera pose estimation, and then finally depth reconstruction. And Duster was saying that, okay, now we don't want those manual efforts. We don't want that amount of steps. All we want to do is that give me a pair of images. I use one neural network and directly map it to 3D. So basically, Duster is saying that we just give all those steps with one neural network. And based on these representations, it can, so if you care about some intermediate tasks like depth estimation, relative camera pose estimation, or key point matching, you can still recover those based on these representations. And it really shows impressive results among those downstream tasks. Yeah, it's incredible.
So it seems like a no-brainer to build on top. So what did you inspire it to extend it in your particular direction?
Yeah, it's kind of like, so if you look into the 3D reconstruction pipeline, so for Duster, although it is kind of like end-to-end reconstruction, but it can only operate on an image pair, which means that, so most of the time you usually have a video and you want to do some incremental reconstructions. This is basically the idea came from. So we want this network to operate on a video where we could do end-to-end dense reconstruction. And yeah, this is basically why I want to work on Spann.
And so is that kind of what inspired like the use of the spatial memory, or is it building on top?
Yeah. That's true. So basically, so the spatial memory is kind of like inspired by a lot of research. So it's originally, so for the memory, the concept of the memory network is originally dated back to the natural language processing research, where they use a memory network to do some question answering. And for me, my direct inspiration is from the video object segmentation research, where they are given the segmentation mask of the first frame of the target object, and then they track through the video to track the target object. And to achieve this, they kind of like use some memory networks to keep track of the previous tracking, and then to give you the next frame tracking. And to do that, you kind of like need some accurate correspondence between across the frames of the target object. And this property is really, really helpful for 3D reconstructions, because most of the time we're just dealing with the correspondence and do the reconstruction, right? And this is my main inspiration of using this memory network concept into this 3D reconstruction task to make Spann become really applicable to video.
How about Monster? Because it's not obvious that you can extend a static approach where you just have a static approach to a dynamic case. So how did you get inspired to do it? Because I mean, what you do is basically later on training on dynamic data, but what was the intuition behind it that it might work?
So I think our inspiration is, first we want to dealing with this problem, this like 3D or 4D reconstruction from a dynamic video in mostly feasible way. So this is a very challenging problem, and we'll be thinking about like we will be given some inspiration from some previous work, like they mainly separate these tasks as many subtasks, like depth estimation and camera pose estimation, and doing a very heavy optimization. But what Duster gives us is a kind of a very powerful way to do this like view alignment, like both depth estimation and the camera pose estimation. We're also like trying to dive into the representation and also the global optimization objective of the Duster model. And we found that this representation or the global alignment objective doesn't limit its application into the dynamic scene. So we found it inherently supports the dynamic input rather than just the static input. But we started trying to see, does it work out? Does it work just out of the box? So we try to feel like a dynamic image as input, and it doesn't work very well. So since the limitation or the objective for the global environment that actually support this dynamic input. So we've been thinking about this could be a data problem, and we fine-tune it on some dynamic data, and it surprisingly work.
You're talking a lot about the geometric first approach. What does this exactly mean?
I think it's pretty simple. Like it means like we only estimate the geometry from this given the dynamic video. And so what in contrast will be also estimating the motion of this dynamic thing. Say like how each pixel moves with time. Like some forms of motion will be like optical flow or like just 3D tracking. But while we are taking this geometry first approach is also pretty simple. Like we don't have many supervision data for training the model to learn the dynamics. So that's why we take this geometry first step.
And how about Spanner? So trying to balance like an efficiency between you have a lot of inputs, right? And you have it's very memory intensive. So I think the key here to get a reconstruction which is continuous is the spatial memory approach, right?
Yeah, it's true. Yeah, so basically our approach is kind of like given a video, we kind of like have a spatial memory to keep track of the previous predictions. So, like as the time goes, this spatial memory will keep increase with over time. So in that case, what we want to do is kind of like, we want to maintain a compact representation of this spatial memory so that it won't explode or just run out of memory. So the key idea here is that we divided this spatial memory into a working memory and a long-term memory. So this working memory is basically for each incoming frame. We will firstly measure the correlation between these new memory features with existing memory tokens. And if the similarity is less than a predefined threshold, we'll inject this memory tokens into our working memory. And once this working memory is full, we also get a long-term memory, because each time we want to do next frame prediction, we kind of like need to query information from this whole memory block. And so our long-term memory is actually a sparse memory, because each time when we query this memory, we can actually track the accumulated weight of each memory tokens within our long-term memory. So based on this cumulative attention weights, we could kick out those memories that hasn't been used that much during the running of this framework, so that we could maintain a compact representation of this memory. So for each next frame, we only query this memory frame once, because the original data is really powerful. Our memory is mainly served as a hint to the model that's which coordinate system you should be in and where you should reconstruct the target scene of the next frame. Yeah, it's basically like that.
Right, because originally when Duster first came out, it was very, very memory intensive. That this isn't something that you'd really be able to scale to even more than like 50 images. I think was kind of like that consumer endpoint. But now you've been able to kind of show like how you can further optimize it and make it just a bit more effective for consumers. And on that other side too, for Monster, you kind of alluded to having access to a large repository of dynamic, trading data. How exactly did you get around that and, figure out a way? Because there's not a ton of data in the world on this.
I think the core idea of why it works is like the task it needs to learn is pretty simple. So for Duster, it will assumes that all the regions or all the pixels from the pair image input can be leveraged to do this view alignment. But our Monster you tell the Duster that there are some specific region, like there's dynamic region, you can ignore them when you are trying to align the two views. So in that case, the task events is pretty simple, and that's why I think with only very few data, like I think the fine tuning is only takes 1 day on like 2 modern GPUs, can can enable the Duster to work on like dynamic things.
And for Spanner, I'm wondering because currently you have like also like, I mean, it's not dynamic, but you have a continuous sequence of images. Would that also work if you would input a random sequence? Is it important that you have a continuous sequence for the memory? Does it make any difference?
Yeah, actually, it really depends on the overlap between the views. Let's say if you only focus on, let's say, target view, like if it's just a single object, then the random sequence or the ordered sequence won't matter because ideally we are not a real SLAM system, so we don't have the prior on this trajectory smoothness. So actually, it's purely based on the previous reconstruction. You incrementally choose the next reconstruction. So if it is object centric scene, then it doesn't matter if the sequence is in random or just ordered sequence.
So maybe we can talk about the curriculum strategy, training strategy. What inspired you to do this? Is it like the issue that you are short on GPU memory?
Yeah. It's basically, so if you want to train Spanner, so basically because we operate on video, you cannot input all the frames into this memory because we got a limitation of the GPU memories. So ideally, we can only insert maximum amount of frames, like it's limited to 5. So if it's more than that, it will running out of memory. So for this curriculum training strategy is basically, so we cannot just input 5 adjacent frames because it will only cover a limited spatial region. So what we do is actually, so at the beginning, we randomly sample 5 frames from the video sequence with with a predefined maximum frame interval. And then we gradually increase this frame interval so that your model can see more spatial regions within this 5 frame, so that your model can actually learn the short-term matching, short-term dependency, and also long-term dependency. And this is basically a strategy for us to overcome the limitation of GPU memory constraint, and at the same time, let the model to learn both short-term and long-term dependency across the video frame.
So, I mean, I think you describe also in the paper that you are using a lower resolution images for training. So you have not the same resolution for the images like in Duster. This is, I think, also a limitation of the GPU VRAM.
Yeah, that's true. So like in Duster, they got a 2-stage training. So first stage, they will use 224 images, like with images with 224 resolution to train. And the second stage, they will increase this resolution. But for us, we can only afford first stage training with image of resolution of 224. And if you run it for the second stage on our training resources, like 8v100, it takes a month to train actually. So
and in terms of Monster, so you were lacking of the training data, which is basically you need like dynamic data, which is annotated. So you were also using synthetic data, right?
Yeah, exactly.
So you had like different data sets which you are using, which were ready, which are open or open source, public, can use them. So, but did you also create your own data set, or did you use just free available data?
No, we only leverage the public data set. So I think there are 3 synthetic data sets we were using. So one is Point Odyssey, second is Titan Air, and third is Spring. So there are definitely some other, like 1 or 2 other data set we can leverage. But what we're caring about is like the data coverage. Like we want the data to cover as much distribution as possible. So it's not about the amount of data, but the coverage of data. And we also leverage one realistic data set, which is the Waymo data set. But though it's very like domain specific, like yeah, mostly like autonomous driving or driving things.
Did you also try to do some dynamic reconstructions of autonomous driving? So do you have also examples from this area? How does it work there?
I think one friend of mine is trying to adapt MonST to some dynamic things, and I think it was pretty nice.
Yeah, no, I wanted to go a little bit more to like the technical detail too, surrounding like the global optimization framework within Monster.
Yeah, so I think this is also the problem of the Duster. Like we'll be given and this is specific for like Monster. Like we will be giving a video input, which is definitely more than 2 frames. So we will design a sliding window to go through all the frames, and within each sliding window, we will sample all the pairs, and then we can accumulate all the pairs of all the windows. And based on these like intermediate pairs, we first run MonST3R across all the pairs to get some like pairwise point maps, and also we will run a off-the-shelf optical flow methods to get the optical flow of all the pairs. And based on these intermediate results, we will run a global optimization, which are basically based on 3 objectives. So first one is the alignment loss, which is the same as the duster, that we will optimize a per frame global point cloud to make it like aligning most with all the pairwise outputs. Yeah, we also, like as mentioned before, like we found this loss can be also support the dynamic input. Like there's no constraint on like you can only apply this loss on static things. So we also apply this loss for our like video input. And the second one will be the flow loss. So we will first like we will like predict the per frame point count, which basically the depths, and also a per frame like camera pose. And based on the point clouds and based on the per frame depths and also the camera pose, we can actually compute a induced flow, with the induced optical flow based on this, and for the static region, and we can compare this with the off-the-shelf like optical flow methods to constrain these like camera pose and also the depths to optimize the camera pose better. And also the last one will be a more handcrafted a optimization loss, which is basically trying to ensure the smoothness of the camera trajectory.
So for both of you, point maps are something that's like very important to the method. Would you mind just giving a quick overview of what a point map is?
So basically, I think the main difference between point cloud and point map is that, so for the point map, it emphasizes on that it got a direct 2D and 3D correspondence. Basically, you got an image and you will get the corresponding 3D point map. And for each pixel, it will have a one-to-one correspondence between this pixel and its corresponding 3D coordinate. And like a lot of 3D vision tasks is based on those correspondence. You can base on this correspondence to solve something like camera pose estimation, intrinsic estimation, and stuff.
For Spanner, usually in Duster, you're doing like the local alignment between image pairs, right? And then you do the global optimization in the end.
Yeah.
But this step is entirely skipped. How do you manage to resolve this?
Yeah, it's basically, so if you look into the data, it's more like so for a video sequence, they will like have a dense graph where each pair of image they will put it into the network to have a local reconstruction, and this local reconstruction will be expressed in the coordinate system of the first image in this image pair. So they will construct a dense pairwise graph, and then they will select the pair with the highest confidence, and then do a global alignment on those pairs to kind of like recover those 3D geometry in a common coordinate system. And for us, we kind of like saying that, okay, now we don't actually want those optimization bit. So basically, the main idea is that once you got new frame, you actually know what the previous reconstruction is, and you can have some relationship between new images and your spatial map of previous reconstruction states. Just based on this relationship, each new frame came in, we got a new reconstruction and also a memory state to keep track of this reconstruction, so that once you got next frame reconstruction, you can reconstruct a new frame based on this spatial memory. So it's kind of like reconstruct the scene in this autoregressive manner, so that you don't actually need those optimization based technique. It would be a purely end-to-end reconstruction from videos to 3D reconstruction.
How does it work for MonST3R? Do you also have like a global coordinate frame, or do you have a local coordinate frames? How do you do the dynamic reconstruction?
Yeah, I think it's a similar as Duster. Like our pairwise prediction is also at the local coordinates, and our global alignment result is based on the global coordinate.
So it's basically also limited to the number of input images, right? So it inherits the same limitations.
I think if you are trying to do a window-wise optimization, it can support like unlimited long videos. Like basically you can optimize a window each time. Because we are sampling like the sliding window across the video, so we can I think it's unlike the Duster, which are based on like very dense really dense graph. So I think for our case, we can implement like a window-wise optimization, and this can support like unlimited long video.
How about new objects which are coming into the scene? Is it a problem or?
Yeah, I think this key of our work. Like for the dynamic objects, we are already doing this like view alignment for the pairwise output. So our pairwise output can like implicitly learn what is dynamic and what is not, and only do this alignment based on this added region. So based on this, like all the pairwise output, since they already align the two views, and ignoring those like dynamic things. So when we are doing this global optimization, we also do not care about like what is dynamic and what is not.
Okay, because I'm just wondering, sometimes when you see the rendering or the scenes, and like with the grandma which is running through the scene. So when you see the reconstruction in this case, and we will see it now like here. So what caught my interest is because you have already the dynamic, or you have the static reconstruction of the scene, right? So it's kind of there, and then you see just the moving point cloud. And how does it work actually? Because if you do pairwise alignment, you wouldn't have for the first frame the entire scene reconstructed, right?
Yeah. I think it's the way we visualize all our results. So there's also one thing I need to mention about work is like once we have this all the perfect like camera pose and also a perfect depth map, we can actually like compare the induced flow of our predicted results and also the off-the-shelf object flow, and we can compare them to get some kinds of like a dynamic mask. So these can actually help to distinguish like which really is dynamic and what is not. And for our visualization, we will first like stack all the background or the static point clouds, and also and only visualize the dynamic point cloud for each frame. Yeah, and that's how you can see the visualization of the running granny. Yeah.
And on the other side of Spanner, one of the really interesting things too, as you're talking about like being able to iterate over each frame, is that this is happening very, very fast. This is happening, within real-time rates, correct?
Yeah, that's true.
And so, as of like right now, like is it kind of like hitting like 50 to 60 frames a second, or where does it come in at?
Yeah, I think it's over 50 FPS for 14-net GPU.
Right, which is just insane.
Yeah, I tried it running on my GPU. I have a 4090, and it had something around 60 to 65 frames per second, which is very impressive. And I was introducing in the beginning that it's kind of comparable to SLAM approaches. So is it something that could potentially replace SLAM, or is it something that enhances SLAM, or how do you see it in the relation to SLAM?
I think that is a quite interesting question, because I've discussed with my supervisor about it. So I think so. Ideally, so currently, so the performance of the spanner make it more suitable at the front end of the SLAM, where you can actually get the dense reconstruction with the corresponding camera pose really fast. But I think in the end, it would be really interesting if this approach can somehow replace or even a comparable approach to the SLAM. But I think the problem lies into the unbounded nature of this 3D world. So basically, for SLAM method, you can use some optimization-based approach to really like do a city scale SLAM stuff. But in our case, because we kind of like share the same feature of Duster, where we directly train our network in a 3D space with 3D points. That means that if you really want to make it a continuous SLAM system, let's say if you move from my room to another room, or even further, then the corresponding point coordinate will be larger and larger, and gradually it will be, like your neural network cannot handle those. And I think this is a super interesting question, because I think we need to think of how do we parameterize this 3D world, this 3D coordinate, to really train a neural network that can run end-to-end in an unbounded scenario. And I think in that case, our method is kind of like, we could say it's somehow like a SLAM system where you can really explore the continuous region and stuff. And also another issue is that we actually don't have any like boundary adjustment or loop closure. So it's basically just reconstruct on the fly. So it will be quite interesting if we can refine our spatial memory, those memory features, to achieve something similar to SLAM, the boundary adjustment, where but I would say I would more like to see some neuron-based approach where we just use neural network without all those boundary adjustment optimization, just with some neural network to fuse those memory, to update those memories to give you better performance. And also another problem is the loop closure. So really for the SLAM, you kind of like your trajectory might make a loop. When this loop closing, you can refine all your previous predictions based on this loop closure. And I think this is something really interesting, is that how do we incorporate this loop closure feature in current Spanner? Because currently it's really hard, I think, for Spanner to involve those loop closure issues. It's the limitation both in like training stage where you kind of like you are constrained by only 5 frames. It's almost impossible for 5 frames to let the model to see those loop closure and stuff. And also how you, during the test time, how you can include this loop closing feature into this standard would also be a quite interesting topic. Yeah.
So it means basically that a current limitation is one that you don't have loop closure. So if you go into another room, it would start to drift, I guess. And also, what is the scene extent, or what is the constraint on the how big can you scenes get so until this fades?
I think that is quite interesting. It really depends on the scene type. So I think for the indoor scene, 1 room is really enough, because if you think back to our curriculum training strategy, we always assume the first frame will be the reference coordinate system. And the spatial region we can cover is this 5 frame. The maximum amount of region this 5 frame can cover will be the maximum of frame where Spanner can handle. But if you look into the, let's say the code 3D, it's outdoor scene data where they actually have a unbounded nature, they are something far away. And in that case, it can handle the object-centric scene fairly well, because 5 frame usually cover a lot of region. But for the indoor scene, if you go from this room to another room, then I think most of the time Spanner might fail. And the current way to deal with that is actually you just restart your spatial memory after a set of spatial region. So every time once you reach some predefined spatial region, you can just restart this Spanner, and then you can redefine the coordinate system of that particular frame, and start from that frame to do the rest of the map. So it's kind of like the sub map based method in SLAM.
So I guess Monster has the same drifting problem, so that it's seeing drifts after a certain amount of frames.
I think Monster is a little bit better in dealing with the drift, because it has this like global optimization stage. But we are also trying to fix this problem by like trying to expand the window size. Like remember, we need to like have a sliding window to go through the whole video. And one thing we need to trade off is like we cannot sample like all the pairs of a very large window, because in that case our like GPU memory cannot handle it, cannot fit in. And so, but we also trying to say we want to increase the window size, because there will be always or usually occlusion appear in a dynamic video. So what we're doing is we try to sample the pairs like with a certain stride from the sliding window. In that case, we can have a relatively larger window, but it can still fit in our like GPU memory. Yeah.
So we kind of have gone through the, both Spanner and Monster, and while both individually can do these incredible things, is it a possibility that the two could kind of coexist and collaborate to create another method?
I think one very straightforward way is we simply like fine tune the Spanner with Monster's like dynamic data. Yeah, but I'm not quite sure whether that's gonna work because I think there could be like some domain drift issue. Yeah, but not sure what Heng is thinking about.
Yeah, I think Jia and I have a discussion like back in September about how to like can we like do this memory networking in the Monster stuff in the dynamics. So actually, there is a paper called Spatial Tracker in CVPR 2024 where they kind of like deal with the 3D point tracking feed forward manner where they give them input RGB images. They will recover the 3D trajectory of each key point in this video. So I think this approach, and also probably we could we could like just like those, we could probably include this memory network scene into dynamic scene reconstruction to make it a feed forward manner, just like spatial tracker. But an interesting question is that in that case, your spatial memory should have a notion of this object type. Let's say, so for indexing, the wall should never move, right? And for object, let's say this pop, it only got some rigid motion, so it won't have some non-rigid motion. But if you have those toys can have some non-rigid motion with some topology change. And also, whether this object can move by itself, let's say this toy, it won't move by itself, right? It will mostly stay static until I put my hand on it to make it move. So this is something spatial memory need to keep track of. Once it encodes this scene object type or this scene structure into this memory, so this object might remain static for the first several frames, and all of a sudden it starts to move. The model should distinguish whether this is because of the camera motion or this object itself. So I think it would be really, really interesting to see whether spatial memory can actually encode those prior information into it and deal with this dynamic scene reconstruction on the fly.
What are the toughest technical challenges here? I mean, usually you have like the memory limitation, so you cannot like, as you said, you have a 5 window frame of short-term memory you are tracking. So if you want to extend it like for longer scenes and so on, is it like something you think can be solved, that you just reduce the memory requirement here, or what are the technical challenges you are seeing besides just modeling if something is static or dynamic?
If you want to extend it to a long video sequence,
for instance, because then you have like, let's say you have a YouTube video like of 4 minutes or so, and you want to reconstruct it, so you have a 3D representation, and you can maybe add something or change it or whatever. So there's like a limitation to the length of the video until it starts to degenerate, right? So what are the technical challenges?
Yeah, I think that is something. So probably what stuff is that this is basically just because of the I think as I mentioned previously, because of the parameterization of your scene, because it is an unbounded scene. So you need to think of a way to how to encode this 3D coordinate in a limited space so that you won't let your prediction be out of the range, right? So so I was previously thinking about this question. So one potential like direction would be how you can use some LLM to actually map this 3D coordinates into a higher dimensional space, like the space of LLM, to help you to address those challenges. So I think you guys might see that. So for the ChatGPT, it may not know whether 3.8 is larger than 3.19 or something. But generally speaking, those LLM should have a notion of which one is larger, which one is smaller in its own its own higher dimensional embedding space. So I think it'd be quite interesting to see how we can deal with this unbounded nature of this thing. And for the currency, I think the tempo solution would be just like during the test time, you build up some submaps and then align those submaps on the fly. It still would be something like a SLAM system without the need of the offline optimization based approach.
Would you see like any advantage to extend it as a Gaussian splitting approach, or I mean, currently it's a point-based approach. Would it help in certain case, or is it just, I mean, doesn't matter?
Yeah. I think it would definitely be interesting to extend it into a Gaussian splitting SLAM. That's it. So, because when I release the code, a lot of people are actually, so like a lot of people caring about how to recover a high quality radiance field from those scene representations and also camera pose estimations. So I've implemented something to directly to make the current spanners support the Nerve Studio so that you can apply some Gaussian splitting into it. And at the same time, I was thinking, so if you look into the Gaussian splitting SLAM from the Andrew Davison's group, where they kind of like can build a Gaussian splitting SLAM on the fly on the monocular sequence without any without any depth measurement.
Mm-hmm.
And it will be quite interesting to see if Spanner can serve as a front tracker so that you can build those submaps with Spanner really, really fast and then initialize Gaussians from that, and so that you can create a submap-based Gaussian splitting SLAM. And that is where you could actually involve all those bundle adjustments, all those closures techniques into this method, which would be quite interesting.
And how about Monster? Do you see any potential to turn it into radiance field? What would it enable? What it currently cannot do?
Yeah, I think it's a bit more tricky for like dynamic sync, because I think we don't have a very good representation for these like 4D sync. Like there are some attempts in like dynamic nerves and also dynamic Gaussians. Like there are tons of work on like 4D Gaussian splitting. But I think our constraint is like we'll be given only a monocular view. So in that case, monocular view cannot definitely like cover all the things, and especially when the dynamic object is invoked. So I think if we want a very very plausible 4D reconstruction result and of like a radiance field or something, we might need some ability to hallucinate like what is unseen and what is occluded.
Okay, and any idea? Could you extend it? So is it possible something that's kind of
Sure.
come in the near future, or is it something which is like, let's say 5 years?
Yeah, definitely. Yeah, it's definitely a very interesting topic. So I would say probably a more suitable 4D representation for like monster-based result is like dynamic 3D Gaussian or 4D Gaussian, because we initially give this like point cloud output, and it's easier to like build a like Gaussian splitting on top of the point clouds. And in terms of like how to hallucinate these like unseen region or occluded region, I think one way is there's a reason word called like Wonderworld, which is from Jiajun's group, and they are trying to basically like they will use a like diffusion model, image diffusion model to render based on the like depths or based on the like point maps. So I think one way is simply trying to include its image diffusion model to hallucinate some unseen region and the occluded region.
Actually, we have a paper called Morpheus from this year's CVPR. We also dealing with dynamic scene reconstructions, and it's basically RGBD based dynamic scene reconstructions, where you can firstly extract if you got the object mask of the target object, you can actually define the camera coordinate system into the target object itself, where you can firstly use some robust ACP to factorize the rigid motion, so that this scene become naturally object-centric scenes. And in Morpheus, we kind of like involve some diffusion wires just to sample some virtual views, like extend the 360 degree to build up dynamic scene representations with 360 degree reconstruction. It is used diffusion wire called 0123. So I guess it would be quite interesting to see if MonST3R can serve as a scene pair, because our method is RGBD based method. So it would be quite interesting to see if the MonST3R's point map will serve as a good initialization for those line of methods where you can actually define the rigid motion, like the coordinate system on the target object itself, and then complete the unobserved region with diffusion phi. I guess it would be quite interesting.
Yeah, sure. And I think this 4D reconstruction can also help the output of MonST3R, because currently we don't have a very specific constraint, only like smoothness of the point clouds or the smoothness of the video depths. But if we can have this, it's basically like motion representation, which can also definitely constrain the smoothness of the video depths or the dynamic point clouds of the master's output, which can even further improve master's results.
It's pretty incredible. The I guess it's kind of a recurring topic, but it's really, both methods are insane. And so there's all this excitement about like how this could be deployed in the real world and what these applications are. Is there a particular like use case or application that you've had for each one of your methods to be used?
I think for the dense reconstruction, it generally like can be applicable to both, because for both MonST3R and Spann3R, we kind of like do not have so much prior information of the scene, so it can enable the users to obtain the high fidelity 3D models from some casual videos, where sometimes from the internet you don't have the prior information about the camera intrinsics and stuff. And also we are dealing with static scene, and also MonST3R is dealing with dynamic objects. So I think that would be quite interesting. So that for the normal users, they can create their own 3D modeling based on those casual videos. They don't need to have any domain specific knowledge about this area, but they can directly use our method to achieve those kind of stuff, which would be really, really cool, I think.
So what me particularly excites, because we were talking with this about the Stern master with Jerome and Vincent, and you probably know the Scanniverse app, right, where you can just go around and scan your environment. But what you see is basically like a very blobby, blurry point cloud or something, like, because it starts processing the Gaussian splatting. So what I see for your approach is like, you can combine it, for instance. So my vision would be, you can just go with your smartphone and scan, and what's currently not available in any approach that I'm aware of, that you just see what you actually have reconstructed, right? And that you can just like fill in the gaps by scanning further with your device. And also, if you have this, then someone is running through the image, right? Which you have sometimes, like imagine you're in a big cloud, and then you have this dynamic aspect. Someone enters the scene and you can start scanning, and you have this on the device, and it's not like a blobby mess, just a real crispy reconstruction. There's something which excites me, and I see this kind of coming up with your approaches. So what are the use cases you are mostly excited about?
Yeah, I think for MonST3R, there are also a very interesting application in terms of like robotics. Because currently, like, I think it's being shown that if you have a explicit 3D representation for robotics, it's much easier for them to learn policy compared to only RGB input. But the problem of the robotics is like currently there's not a very good way to get a very robust like 3D or 4D reconstruction. And I think that's this is a benefit of the Duster or these kind of extension works. Like you can have this very generalizable or robustness ability to reconstruct a 3D or 4D scene in any kind of like area. So I think this could be a very big plus for robotics, especially like for them to learn policy and in very like different kinds of setups, different kinds of things.
Yeah, and for me, I was thinking of something like so currently, if you look into the architecture of the Spann3R, it shares a lot of similarity to LLM and also 2D foundation models. So can we actually build a unified representations with all those information into just one unified representation? Let's say if you do a city scale mapping with a spatial memory, a unified memory stuff, and once you are in a self-driving car, you just give your car an image and with some descriptions that you may not know that place, but you can have some blurry description of the scene, and you just need to input it into an LLM, and it will just encode this image and also the language instructions into unified representation or unified embedding space, and curate the spatial memory to find out where this image is at, and then this car just drive you to that place. I think that would be quite interesting to feel, but I'm not sure. Maybe it's just too early to think of those applications. Probably, yeah.
Well, so let's talk about some of these like potential advances, because it's pretty crazy and mind blowing to think about that these things are actually achievable over a given period of time. And so on the side of robotics too, one of the really main talking points right now for NVIDIA is the move into physical based AI systems that can understand the physical world. And I do think that these technologies have the ability to serve as that underlying framework for robotics and other applications that take place within the physical world itself. But what do you see as the biggest remaining challenges in the world of 3D reconstruction? And as an extension of that, where do you see it heading once some of those issues are solved?
The biggest issue is like we are still using a data-driven approach to handle all the kinds of like 3D reconstruction, like different subtasks of 3D reconstruction. Like for Duster or these kind of extension, we still need or other like marker depth estimator. We still need a data-driven approach. But once you are using a data-driven approach, you will surely like run into a problem of like out of domain or out of distribution. Like you cannot like collect all the data of this world. So I think one definitely very important question is like how can we make this kind of approach to generalize beyond the training data set or training data distribution.
Yeah, I think probably this is something where like probably embodied AI is about. So if let's say if you consider you got a robot agent is walking on the street, if you incorporate this one with some physical like 3D foundational models and also some multimodality models, and you just let this robot work, and this robot might have some built-in sensors like MMU or GPS to give you the precise locations of this robotics. And once this robot is working, the visual observation will change. How can we just leverage those kind of information to update our like 3D physical models, like 3D foundation models, instead of like, because as Jin said, currently we kind of like relying on those post RGB images, which is a huge limitation, because if you think about LLM like ChatGPT, it basically can learn can perform some self-supervised learning from the web scale data. But in 3D community, we kind of like limited by the data itself. And also, as I mentioned, that also is because this is an unbounded nature of this 3D world. So we need to think of the way to parameterize this scene to really make the network being able to train like unbounded manner.
Given the advancements based on Duster and or maybe similar approaches, do you think like the traditional approach, the traditional structure from motion pipeline, or like more traditional Gaussian splitting, where you have like you compute the point cloud first and then you do the optimization afterwards? Given that you want to apply it to real-time cases, do you think this is something that's slowly dying?
I think for the real-time, I wouldn't say it's slowly dying, because I still believe that optimization-based approach is really, really important in this field. Because so for the learning-based approach, it's basically serve as a prior. Let's say for human, you kind of like can say that which object is far away, which object is near, but you cannot precisely define a metric prediction actually. So for me, I still believe that the learning-based approach was still limited by some position where you need to align this gap with those optimization-based approach in order to achieve a really incredible 3D reconstruction. This is why you still see those co-map models they are still the state of the art model because of those optimization based approach. But eventually, I think learning based approach will always serve as the first 100 meters. Let's say it basically gives you a good enough initialization so that you can only perform several optimization steps. Just like I think in Monster, they only have a few optimization steps to actually give you the dynamic scene reconstruction. So I would say probably in future it will be more like a hybrid approach.
Yeah, I totally agree. Like, this is just like when you are trying to scale a large language model, you have two ways. Like one way is to scale the training time, another way is to scale the inference time. So for me, like when you're trying to like add more data and add more like larger architecture, it's just like scale the training time. But for optimization, to me, it's just like scale the inference time. And I think these two ways can be mutually beneficial to each other. Like you can both scale this training time and the inference time. So that's why I think these two are both important.
So as we are approaching the end of the episode, I would like to ask you, because there's like so much input currently in this field and so much pace, right? Everything like evolves pretty quickly. If someone is new to the field, wants to do some research, how to start?
I think probably you need to think from a unique this perspective about this approach. Because currently you've seen a lot of like amazing Gaussian sliding paper built on top of the dataset. But one problem with the dataset is that it's kind of like, although it is good that it doesn't require some intrinsic parameters prior like geometry constraint, it can naturally recover the intrinsics after some optimization steps. But the problem here is that once you want to adapt this model to a new task or new data distribution, then you need to think of that if you fine-tune this model into those new data domain, then you might lose some information about its original ability because it's trained across multiple data sets where they kind of like learn some intrinsic prior from that point. So this is something people need to think of when they apply this method to some new task or start to do some research about it. Is eventually if you just overfit this model into some let's say some limited data set, then you actually lose the ability of the data for their amazing generalization ability across different tasks. So yeah, I guess this is quite important to think. So how do you make data to be able to achieve some new task without losing the generalization ability of its original approach?
Yeah. Like for me, Monster is my first 3D or 4D project, so I definitely like spend a lot of time to identify the topic and the project. So it's actually to me, honestly, it's a really tough experience. So when I start this project, like trying to do a little bit 3D or 4D, I think most important thing to do is trying to learn some foundation knowledge about this field, like some 3D and 4D. Like I need to date back to where the stereo images and the stereo very old stereo methods to get a very good foundation of these kind of field. And later, I think another important thing is trying to like keeping pace with some reason approaches. So because the field is moving really fast, and you need to get to know what is the frontier or the age of this field to get a view of what could be the possible future and what is valuable in the future. Yeah, so yeah, I think that's my advice. Like you need to first look back into the foundations and also trying to keep up with the age.
Awesome. Michael, any further questions?
No, I think that really, takes us through the episode today. So yeah, thank you both so much for joining us and talking about both Monster and Spanner. It's really incredible to see that, like we were just mentioning, the pace of evolution within this technology, and we're really excited for the future. So thank you both so much for coming on, and we will return next week with yet another episode. So thanks so much, everyone.
Thank you very much for joining us.